Protection and control systems are the core of any electrical substation. They are not simple auxiliary devices, but critical mechanisms that must react precisely to any electrical fault. When these systems fail, there is not only technical risk, but also economic and legal risks. Understanding their operation and keeping them up to date is key to avoiding serious consequences. Redundancy is essential. The N-1 and N-2 configurations ensure that even if one component fails, another can take over. In critical substations, this double protection is mandatory. However, many installations fail to comply with annual verification, increasing operational and financial risks. Relays, responsible for 40% of incidents, are vital for detecting and isolating faults. Circuit breakers, 25%, perform physical disconnection. Control systems, 20%, and communication systems, 15%, ensure coordination between all elements. If any of these components fail, the impact can be immediate and costly. Among the most frequent failures are incorrect calibration, which generates unnecessary trips or a lack of response to real faults. Relay aging, which produces silent errors. Unwanted trips due to interference, with a direct impact on service continuity. And a complete lack of protection, the most critical situation, where the system fails to respond and damage worsens. To prevent these risks, it is essential to conduct comprehensive functional testing, perform fault simulations, and maintain clear documentation. Continuous monitoring of equipment status, operating times, and self-diagnostics helps anticipate problems. Furthermore, updating technology every 10 years, integrating IoT, and strengthening cybersecurity reduces exposure to threats. And of course, backup systems must be operational. At least one backup is mandatory, at least 2 backups are ideal in sensitive facilities, and a hot standby configuration is a safeguard against sudden failures. In short, these systems don't fail frequently, but when they do, the impact can be devastating. Investment in maintenance, redundancy, and upgrades is not a cost, but a barrier to much greater losses. As for insulators, they are essential but often overlooked components, whose degradation can lead to serious electrical failures and considerable economic losses. Although they are not as prominent as transformers or switches, their role in electrical insulation is key. When they lose their properties, partial discharges, loss of dielectric strength, and unexpected disconnections can occur, resulting in service interruptions and costs due to penalties or emergency interventions. The location of the substation is a decisive factor. In coastal saline areas, degradation reaches 78% due to salinity and humidity, while in industrial areas, it is 65%. In desert climates, it reaches 52%, and in moderate environments, it drops to 32%. These differences should determine the frequency of inspections and cleaning strategies. As not all locations face the same risks. Technically, the dielectric strength of insulators decreases between 1.8% and 6.5% annually. Above certain salinity levels, more than 300 milligrams per square meter per day, deterioration accelerates. Factors such as UV radiation, 30%, pollution, 25%, humidity, 20%, temperature, 15%, and electrical discharges, 10%, act together, progressively weakening the material. Solar radiation damages polymers, generating microcracks and loss of hydrophobicity, which favors current leakage. Surface contamination with moisture forms conductive films that cause partial arcing and erosion. Detecting these failures in a timely manner requires predictive inspection, visual, thermographic, ultrasound, and dielectric measurements. Preventive cleaning with distilled water and no harsh chemicals is essential to preserve the insulator's integrity. Indicators such as tracking greater than 5 mm, hotspots greater than 5 degrees, corona effect greater than 40 decibels, and surface resistance less than 70% alert to critical conditions. In short, insulator degradation can lead to invisible failures that are not perceived by the SCADA, but have a direct impact on operations and costs. Incorporating systematic inspection into maintenance and prioritizing assets in critical areas is key to avoiding costly surprises and improving overall system reliability. The SCADA system is the operational brain of a photovoltaic substation. It coordinates control, monitoring, and remote operation, allowing real-time response to failures or changes in conditions. Although its availability typically exceeds 99.5%, that small remaining fraction can cause critical interruptions if effective backup is not available, leading to production losses, penalties, or regulatory noncompliance. Today, the main risk is cybersecurity. Integrating more connected devices increases exposure to threats such as industrial malware, unauthorized access, and data manipulation. These incidents can compromise complete system control and lead to serious operational downtime with direct financial impacts, including recovery costs, damaged reputation, and legal penalties. Added to this are communication failures between RTUs and the control center, interference, or signal degradation. The loss of visibility forces operations to operate in reactive mode, increasing costs and reducing efficiency. Likewise, hardware failures, such as server downtime or loss of databases, lead to manual modes that affect traceability, KPIs, and the ability to perform technical and financial analysis. Another risk factor is outdated software, which leaves many plants without support, without security patches, and with compatibility issues. Urgent updates when the problem is already active are much more costly than preventive planning. To mitigate these risks, robust measures are required: multi-layer firewalls, dual authentication, segregated OT/IT networks, and continuous monitoring. Furthermore, periodic testing, such as monthly switchover, data verification, and recovery drills, are key to ensuring resilience. Backup systems, such as hot backups and full server redundancy, allow operations to continue even during failures or maintenance tasks, reducing technical downtime and improving overall availability. It is vital to monitor critical alerts, prolonged communication interruptions, unauthorized access, performance degradation, or system failures. These signals should not be ignored, as they predict major failures with technical and economic consequences. In short, although SCADA systems do not fail frequently, their failure can bring the entire plant to a standstill. Maintaining cybersecurity and keeping these systems up to date is not a luxury, but an essential investment to ensure the continuity, profitability, and sustainability of the power plant. The cooling system, often underestimated, is essential to preserving the transformer's lifespan. Although it doesn't cause immediate failures, malfunctions cause heat buildup that accelerates the aging of internal materials. This silent degradation impacts both the technical performance and the financial depreciation of the asset. Loss of cooling reliability directly affects operational continuity. Failures in fans or pumps disrupt thermal balance, causing overheating that can reduce transformer lifespan by up to 50%. This translates into additional costs for early replacement and a reduction in expected payback. Fans fail due to mechanical wear or electrical faults, which reduces heat dissipation and degrades the dielectric oil. Pumps, for their part, can experience cavitation, blockages, or wear, creating hot spots that damage insulating materials. Temperature sensors, if miscalibrated or contaminated, produce erroneous readings that prevent adequate protection. Heat exchangers are also critical. The accumulation of sediment or corrosion can reduce their efficiency by up to 60%, forcing the system to operate at higher temperatures, which accelerates the wear of all components. The key to preventing these problems is continuous monitoring via SCADA, which records variables such as oil and winding temperatures, fan speed, and system pressure in real time. This information allows for predictive maintenance and prevents major failures. Furthermore, backup systems must be activated in less than 5 seconds and checked daily with a minimum architecture of 1+1. Strict adherence to maintenance intervals: 6 months for fans, 12 months for pumps, 18 months for heat exchangers, 24 months for sensors, is vital to avoid surprises. It is also essential to define clear thresholds: alarm at 85 degrees, shutdown at 95 degrees, automatic backup activation if a fan fails, and low-pressure protection. Ultimately, cooling is not an auxiliary. It is life insurance for the transformer. Monitoring its thermal performance with a predictive approach not only prolongs the asset's life, but also protects the investment and improves long-term profitability.